chapter 2. So, we've been talking at length about heat and how heat moves and the properties of heat. But let's talk about where we on Earth get our heat, and that is primarily from the sun, radiant energy from the sun. So, radiant energy is just the term we use for all heat and light that the sun gives to us that comes in what we call electromagnetic waves. It's called that because the property of light is such that it works on an electrical level, much like electrics, there's positive and negative, but also as magnetic energy. So we'll talk more about that. But light waves travel at shockingly light speed. So what is light? Light is made of photons, and a photon is this tiny little piece or packet of energy. So it's not quite matter, it's more like energy. It's the smallest discrete unit of energy we can measure. And when it is emitted, items that emit it, they need energy. And so we've talked about how temperature is energy, right? The movement of molecules is temperature, is energy. The greater the temperature of something, the more energy it has, the more photons it emits. And when something emits a photon, the photon just doesn't shoot out. It actually shoots out like this. I don't know if you can't tell my microphone is moving up, but it shoots in a wave. Okay? It's just these waves move very, very fast. So if you took all of the energy we get from the sun, they call it the electromagnetic spectrum, because you can actually break that down, and there are several different types of wavelengths that we receive. What we notice most is what we call visible light. So visible light is this part of the wavelength, and what you'll notice is that all of these energies, these photons given off by the sun, some of them have a very long wavelength, very slow, and some of them have a very high wavelength, right? Or actually they call it short wavelength. Very, very much rapid energy. So you'll see terms like cosmic rays, gamma rays, X-rays. These are energies that are given off by the sun that we cannot perceive with our eyes, so we don't see them. If you think about an X-ray machine, you actually don't see the X-rays coming out, but we have special film that can capture that so that we can use that to see through the body, right? Maybe you've heard of ultraviolet or infrared. Infrared energy is usually also heat energy. We can't see it, although sometimes you might see those cameras that can sense heat, right? Microwaves we talked about a little bit, radio waves, these are all parts of the spectrum. But the part that we see, visible light, between violet and red, are just different wavelengths. So that's what makes the different colors, the wavelength of the light beam. So red has the longest wavelength. And by the way, wavelength is just the distance between the points on the wave. So that's longer and that's shorter. So as I was saying, the higher temperature something is, the more photons it gives off. So that's why the sun emits so much infrared radiation, so much visible and infrared radiation, because it has so much more energy. The Earth technically does give off radiation like that, but because we're so much cooler, it's actually usually just heat that is absorbed and reflected. Okay? So when you look at what the sun gives us, the vast majority of energy is shortwave radiation, which includes visible light. So we see that. But we do get a lot of other wavelengths too. The Earth absorbs some of that and reflects it. Now, we've talked a little bit about this before in the atmosphere. The ultraviolet radiation, the stuff that we can't see but can damage our cells with the effects of, say, a sunburn, right? Or causing cancer. That is mainly absorbed by the ozone in the upper atmosphere, so we don't really have to worry about it too much. But how much do we actually get also depends on the atmosphere. Not only the ozone, but if there's a lot of clouds or aerosols, because those can actually reflect it. So again, when we look at this ultraviolet radiation, or UV, right here, C, B, and A, this is the stuff that we can't see but can be very damaging. Okay? Now, almost half of the radiation that the sun gives us is visible. And we don't really notice all the colors because they all come together, combined. And when all the wavelengths combine, our eyes interpret that as sunlight or white light, right? We actually need things to break it apart. So if you've ever held up a prism or a crystal to a ray of sun, when the light enters that crystal, The crystal slows down the light and allows the different wavelengths to separate. That's why you get that kind of rainbow. It's actually the same reason why we get a rainbow in a rainstorm. When the sunlight comes and hits the water, the beam of water bends the light a little bit. It allows it to kind of separate out, and we see the different wavelengths. Now, infrared we don't see, but what we do perceive it as is heat. The energy in the wavelength hits us or a rock or something, and that energy is transferred in the form of heat. So that's why you feel warm on a sunny day. That's why the earth gets warmed up. The soil, the water, parts of the air actually absorb that. All right. So I'm going to say, if you're sticking with me, good job. We're almost done. We come up with this idea that we know how heat moves, we know where we get it. So we have this idea of the energy budget of the earth. So let's start with this. We get our energy primarily from the sun, light and heat, right? Now, the sun gives off light in all directions, so not all of it comes to Earth, right? Some of it goes to other planets, goes out into space. The amount of sunlight that the Earth gets from the sun is called insolation. And this is basically all the light over the course of any given time that the Earth is receiving from the sun, either as light or absorbed heat. Now, not all of that energy works the same way. Some of it is reflected by clouds back into space or aerosols in the atmosphere. Some of it is absorbed by water, and it heats up water or rocks or dirt. Sometimes it actually warms the air. So insolation not only is transmitted to us, but it's scattered, reflected, and absorbed. Now, between us and the sun, the vacuum of space, so there's nothing to stop the transmission. The waves go right through. It isn't until they hit the Earth they encounter something like air, the ozone, which actually slows down or reflects the ultraviolet. Other things that can slow the transmission, now that's my son, he's not happy with his fruit pack. We get you, Henry. We feel your pain.
Henry, just practice with your hand, okay?
I totally get it, buddy. Anyway, things can actually, in space, nothing stops the movement of ultraviolet. It isn't until it encounters something like air in the atmosphere, water, or glass. Those can actually slow or stop different wavelengths. Interestingly, glass, one of the beauties about glass is glass allows light beams to pass through, but it absorbs ultraviolet radiation. That's why you can't get a sunburn sitting in a window. Other things that happen, scattering. Solar radiation, sunlight comes into the atmosphere and it strikes something and it bounces off. Now, if it bounces off in random patterns and no general direction, just all haywire, that's called scattering. And that's what happens if you think about a cloudy day, when you have clouds overhead and you can't see the sun distinctly and there's no distinct shadows, it's kind of a gloomy, diffuse light. That's because the light beams are all just being bounced around. Another way that things are scattered is reflection. If all the light beams bounce in the exact same direction, say off of a shiny piece of glass or water, and they reflect, then you see that pattern. So reflection is when all the light beams bounce in the same pattern. They all come in at this angle and all leave at this angle, right? If you think about a mirror, right, you're actually seeing the light that was coming into the mirror and bouncing back at you. But this is also what creates the colors, because remember we said all sunlight comes in as white light. So how do we see the different colors? Well, think about the sky. Why is the sky blue, right? There's actually a proper technical term. I'm not going to get into that. But in reality, what it is, there are aerosols and chemicals in the sky that absorb different wavelengths. The one wavelength that gets absorbed last is the blue wavelength. It travels the farthest. So all the other colors are absorbed first. And what's left are the blue wavelengths. And that's how we perceive it. The clouds. Clouds aren't always white, are they? The clouds that are white usually are reflecting all the sunlight. Sunlight hits the clouds, it bounces off. So what happens is all the light comes in, all the light comes off. So what do we see reflected? The white light. But what if some of the light is not reflected? That's when you get gray or dark clouds. We've talked a little bit about a rainbow. When sunlight passes through small droplets of water, it actually slows the light down as a whole and allows it to spread apart. So we see the different spectrums. The reason vegetation is green is that chlorophyll absorbs all of the energy from the sun. Plants love sunlight, right? And they use the chemical reaction of chlorophyll to create energy. But the one wavelength they don't absorb is green. And so what happens is light hits a plant, all the sunlight is absorbed, used by the chemical chlorophyll, except for the green, which bounces back. And so that's why we see green. Water is usually blue, but not always the case, because blue travels farthest in water. Water slows down light. It slows down all the other colors faster than blue. And so, generally speaking, the only color that's left is blue, and that's why we reflect it. But there are times if you've seen water that's like maybe light green, if you're on a stormy day, it's gray because all the water is being reflected. Sometimes you'll see water perfectly calm, and it looks like silver because it's reflecting and not scattering the light. All the colors that we see are basically the reflections of light. So we're going to pause right here because it's time for me to go have some lunch, and it's time for you all to kind of stretch up, get up, shake out your chilies, and we'll come back with our next part in just a little bit.